Hi there, this is Math 8, Unit 5, Lesson 2, called Introduction to Functions today. So today we're going to talk about what a function is. So here we go. The first part is called square mean. It says here are some numbers in a list, and we have this set of numbers here. Okay, and it says first of all how many numbers are in the list, and so we just count them up, and we have 1, 2, 3, 4, 5, 6, 7 numbers in our list. Now the next step says make a new list containing the squares of all these numbers. So if we take the numbers, let's take for example 1, and then -3, we have -1/2, we have 3, we have 2, we have 1/4, and we have 0.5. And we square them. To square means to multiply it by itself. So this becomes 1 times 1, which is simply 1. This is 1 times a -3, sorry, -3 times -3, which is 9. If we do a 1/2 times another 1/2, that becomes a positive. 1 times 1 is 1, 2 times 2 is 4, and it's a positive 1/4. A 3 times 3 is 9. A 2 times 2 is 4, right? And then a 1/4 times 1/4 is going to be a 1/16. And a 0.5 times a 0.5 is a 0.25, which is also the same as 1/4. So our numbers here, we have a 1, a 9, 1/4, 9, 4, 1/16, and also essentially 1/4 as well. So how many different numbers are in the list now? We have the 1, right? We have a 9, but that comes up twice, so we can count that one time. A 1/4, so that's 3 numbers. 4, there's another number. 1/16 is there, and this 0.25 is the same or equivalent of 1/4 there. So we would leave it as there being 5 numbers in this list. Now the reason for that is the big question here. Why would the two lists not have the same number of different numbers? What do we do differently? Right? We had an input, we did something, and we ended up with an output as it went through there. In this case here, we squared the number. So as we square these numbers, what we're seeing is that because we take a number like a -3 times a -3, and we end up with a 9, in the same way we take a right +3 times a +3, and we get a 9. The difference here is that I can take a negative number, and when I square it, I can end up with a positive output. So I could put a -3 as my input and go through my little input box and find out I come out on the other side with a +9. Just like with a +3, I can still come up with a +9. So that can happen a couple different times. So what happens is, the reason why is that because a negative number, right, a negative times a negative can be positive. And that's the reason why we have different sets of numbers between the first list and the second list. Okay? So the next part says, you know this, do you know that? Say yes or no for each question. If yes, draw an input-output diagram. Okay, and if no, give examples of 2 different outputs that are possible for the same input. Okay, so if we know a person is 5.5 feet tall, do we know their height in inches? So the question is, can we convert feet and put that in terms of inches? And the answer for this would be yes, we can do that. And that's because if we had an input of 5.5, right, and we put it inside of our little, like our input-output diagram here, if we put that into it, what we're going to do is we're going to multiply by 12. And that will convert feet to inches, and on the outside over here, you end up with 66 inches, right? So 5.5 feet, you multiply feet by 12 to come up with how many inches you would actually have. So it's possible to do that with an input-output diagram because we're multiplying by 12. A number is 5. Do you know its square? Well, again here the answer would be yes. Again, we take the 5 and we're going to input it into our input-output rule here, and we're going to square the number. So square the number, and when you put the 5 in and we square it, we come out with 25. And that's going to work with pretty much any number we got. Okay. The next one says the square of a number is 16. Do you know the number? So the question here is, you have the rule here is I'm squaring it, right? So think of it this way. We're going to square the number, and what comes out in this case is a 16. The question is, do we know what that number is right there? What the number is? Is there a number you could put in that gets you 16? Well, to answer this, we would say, yeah, I know there's a number, but do I know the exact number? I need to be precise here, right? Precision matters in, not in my spelling, but in mathematics. Here's our problem. 4 squared equals 16, but also negative 4 squared equals 16. So because a negative number squared gives me a positive solution, I don't actually know what this number is going to be, because it could be 4, but it could also be a negative 4. I just can't tell from the information given. So in this case here, we would say no, we don't know what the number is going to be. Let's look at number 4. Next one says a square has a perimeter of 12 centimeters. Do you know the area? A couple of key things that are important in this statement. First of all, we know that it's a square. So it's already telling us that because it's a square, all the side lengths are going to be the same. And it has a perimeter of 12. Do we know the area? We would say in this case, yes, we can find out the area. And that's because if it has a perimeter of perimeter of 12, we could then take the we could take the side lengths, the perimeter, take the perimeter, and put it into our box here, and because it's a square, we can divide by 4, okay? That's our first step, divide by 4, and then we're going to take whatever we have, and then we will multiply by itself. Sorry, I ran out of space there. And multiply by itself, or square it, okay? So let's take 12 for example. If we do 12 and divide it by 4, we come up with 3. That's our first step of our rule. If I multiply 3 by itself, or square it, that will give me the area, which is going to be 9. So yes, that would work, and we can create a rule for that. But that works because it's a square, and we can divide it by 4. The next one says a rectangle has an area of 16 centimeters squared. Do you know its length? So again, right, if we took our previous rule, whatever the rule might be, and we got an area of 16, the rule for finding area is length times width. Do we know the length of that rectangle? Either the length or the perimeter, whatever you want to think of. In this case here, we would say no, and that's because it is not a square. In terms of an example here, right, if I had lengths of 4 times 4, or if it was a square, I could have lengths of 4 and 4, and that would give me an area of 16. But I can also have a rectangle that's an 8 by 2, like this, 8 by 2, and that also is going to have an area of 16. So I could have side lengths of 4, side lengths of 8, side lengths of 2. I can't tell for exactly what that length is going to be. 6 says you're given a number, and do you know the number that is 1/5 as big, right? In this case here, we would say yes, because whatever the number is, okay, I'm going to put it into my rule, okay, and we're going to multiply by 1/5, and that's going to give me 1/5 of that number, whatever that's going to be. So yes, I can do a simple rule to find out 1/5 of a number. I multiply the number by 1/5. Okay, you are given a number. Do you know its reciprocal? And again, this one we probably would go ahead and say yes, right? Right. In this case here, we'd say yes. So our number is here, whatever that's going to be, and we would divide by we go here, go 1 divided by the input. Sorry. Our rule in this case would be 1 divided by the input, and that's going to give you 1 over whatever that number is going to be. So yes, we can figure that one out as well. Okay? So that's the idea behind that one here. For section 2.3, this one here is a little bit, maybe a little bit more challenging here. So I'm going to put a little question mark here for whether or not you're going to cover that in class or whether you did or not. I'm not sure if our kids are going to do it over here at Alta, but here's what we have. It says, here are questions from the previous activity. For the ones you said yes to, write a statement like, the height of the rubber ball bounces to depends on the height it was dropped from. Okay, so the height it bounces to depends on the height it was dropped from. So here's a ball, and it goes down, and it's going to bounce up. So whatever this is going to be, this amount depends on this amount right there. Okay, the higher you drop it from, distance you drop it from, the more it's going to bounce. Bounce is a function, bounce height is a function of drop height, right? Meaning it depends on it. The bounce height depends on the drop height, and that's the idea there. Okay? For all the ones you said no to, write a statement like, the day of the week does not determine, right? These are no statements, does not determine the temperature that day, or the temperature that day is not a function. Okay? So function means it depends. It depends on something happening. So if I went back to my notes here, number 1 was a yes, 2 was a yes, 3 was a no, 4 was a yes, 5 was a no, 6 was a yes, 7 was a yes. So a person is 5.5 feet tall. Do you know their height in inches? What we would say is something along the lines of, we could say their height in inches depends on their height in feet. All right, that's kind of the idea. So whatever their height is in inches depends on their height in feet. We could also say the other way that height is a function, height in feet is a function of height in inches. So there's a couple ways to write that one. It gets a little complicated when you start kind of writing them out, like, wait, which way? The order tends to reverse here. Looking back here, right? So the bouncing ball depends on the height. So bounce height is a function of drop height. Okay? So we would say inches is a function of feet. Okay? So we could say, or height inches is a function of height feet. Okay, so kind of two ways of looking at that same problem. We can either say their height in inches depends on their height in feet, or we could say height inches is a function of height feet. So it's hard to kind of verbally say that there, but hopefully you write out, you can kind of see the way it works. Look at number 2. A number is 5. Do you know its square? Okay, so the square of a number depends on the number, is the idea here. The square of a number depends on the number. Okay, so the square of a number depends on the number. So it's another way of saying this is basically the output depends on the input. And that's kind of the key thing here. That's the way a function rule is going to work. The output depends on the input, right? Whatever you put in is going to determine what you get out of it, okay, for all the situations. So the square of a number, number 3, is 16. Do you know the number? Okay, so in this case here, it's a not one. We would say the square of a number does not determine number. And we had that example, if there was 16, 16 can be found by doing 4 times 4 or negative 4 times negative 4. And that's the idea here. So these are all the same kind of ideas as you go through those. I'll let you do this in class as you go home and do your own, and write your own little statements and check them with your teacher. All right, let's look at this section 4. It says same function, different rule. Which input-output rules could describe the same function, if any, and be prepared to explain your reasoning. So we're looking for rules that describe the same function. Let's take a look here. So here are 3 function rules. You have the number 7, you square it, which is 7 times 7, and we end up with 49. Okay. This rule have number 10, find the area given the side length. Okay. So the area would be, if I have the side length is 10, this becomes 10 times 10, end up with 100. That looks very similar to this idea, right? The same number times itself. 10 add 90. 10 add 90 gets to 100. While these are the same outputs, in terms of the function rule, we would say these two seem to have the same function, okay? If we're talking about squares. So we could say same function rule if we are talking about squares, okay? Because that's why this one works. I can find the area of the side length if this is a square with a side length of 10. If this was one of the side lengths of a rectangle, it wouldn't help me. It's not going to be the proper area. So these two seem to have the same function rule. All right. So in summary today, when we look at our summary statement, it says, let's say we have an input-output rule that for each allowable input gives exactly one output. And then we say the output depends on the input, or the output is a function of the input. And that's our big takeaway statement of the day. The output depends on the input. That's the way that works there. Okay, and we have the example of a square. The area of a square is a function of the side length because you can find the area from the side length by squaring it. So it depends, right? The output depends on the input. Okay, whatever I get there depends on what I put right there. All right, and that's the idea. So take a moment, work on your homework, and then we'll go over that together here. All right, here's the homework. It says, here are several function rules. Calculate the output for each rule when you use -6 as the input. All right, let's do this here with -6. So if I put -6 in, -6 in here, and I subtract 7, that's -6 minus 7. When I subtract 7, that's like adding a negative. Signs are the same, so I find the sum and keep the sign the same. I come out with a -13. Okay, so that's the first one there, -13. For the second one, I have a -6. Right, I put a -6 in, and I squared the input. So -6 times a -6. 6 times 6 is 36. A negative times a negative is a positive, so I end up with 36 for rule number 2. Rule 3. I have a -6. I divide by 3. So I have -6 divided by 3, and that reduces down to a -2 for my output at -2. Coming over here, we have -6, and we're going to divide the input into 3. Divide the input into 3. Divide the input into 3. Okay, so that's going to take us here. We're going to do 3 divided by a -6, and that's going to give us in here a -1/2 as our solution. For the next one here, we have -6 as our input, and it says write pi, so I just write pi. There's no math to do there, that's just my answer, is simply pi. And then finally, we have -6. Define the volume of a cube with side length equal to the input in centimeters. Okay, now here's the problem. If this is a side length, can I have a negative side length? The answer is going to be not possible, and so we're going to write down not a valid side length. Yes, I can do -6 times -6 times -6. I can do the math, but I can't have a side length for a cube that is a negative value. You can't have a -6 as a side length. It doesn't exist, okay? So we would say it's not a valid side length. It just won't work there. All right, number 2. A group of students is timed while sprinting 100 meters. Each student's speed can be found by dividing 100 meters by their time. Okay, so speed equals 100 meters divided by however long it takes them to do it. That's how we find out their speed. So speed equals 100 meters divided by the time. So is each statement true or false? Explain your reasoning. Speed is a function of time. Question here. Does the speed at which you travel depend upon how long it took you, the time? That would be true. That's a true statement. And the reason that's true is speed depends on time. Okay. Time, next one here, is a function of distance. Does the time it takes you, does that depend upon the distance? In this case, because it's a set amount, all right, be careful here. Because we're only going to go 100 meters, this is a constant. It's not going to change. That is 100 meters. We're not changing it, so that's not going to have an impact on our time. So in this case here, we would say false, okay? And that's because for each distance, run, there are lots of different times. Meaning this, let's say I had an input-output table like this, okay? And I had 100 meters I ran. Somebody ran it in 5 seconds. Someone else ran 100 meters in 10 seconds. Someone else ran 100 meters in 7 seconds. Because there's nothing consistent happening there, there's not a function rule, is there? It's something different every time. All right, C. Speed is a function of number of students racing. Okay, that's going to be false. Okay, all right, and that's because the number of students does not affect the speed, right? The number of kids in the race doesn't change how fast somebody runs. Either you ran fast or you ran slow. Just because there are 100 people doesn't mean you ran faster or slower, unless of course they trip you and knock you over, and then that's another story. Now D, time is a function of speed. We would say this is going to be true. Okay, and that's because the time a student runs depends on their speed. And that's what we would say there. The time a student runs depends on their speed. However long it takes depends on how fast they did what they did. All right, let's take a look at number 3. It says Diego's history teacher writes a test for the class with 26 questions. The test is worth 123 points and has 2 types of questions. Multiple choice is worth 3 and essays are worth 8. How many essay questions are on the test? Explain or show your reasoning. All right, so let's take a look here. A couple things. First of all, we know that multiple choice questions plus essay questions are going to be equal to 26. There are 26 questions total, so multiple choice plus essay equals 26. We also know that a multiple choice has a value of 3, so 3 times multiple choice plus 8 times the essay. This is our value of our test for 123 points. At this point now, I can decide which one I want to use to plug one of these values into M or E. It really doesn't matter. I'm going to go ahead and choose the M one. So I'm going to say that M equals 26 minus E. So now that I have the M variable by itself, I can plug that into this equation here to solve for, in this case, solve for E. So we're going to say 3 times 26 minus E plus 8E equals 123. Okay, so now to solve this, I need to do some math here. Got to move some things around. I'm going to move down here if you don't mind. So 3 times 26 is equal to 78 minus 3 times E is 3E plus 8E equals 123. All right, I can combine some like terms there, so I have 5E with those. I'm going to go ahead and subtract 78 from both sides, so that goes away. And so 5E is going to be equal to, in our case here, 5E is equal to 45. Okay, and to solve for E, I divide both sides by 5, so that E equals 9. That means there are 9 essay questions on the test. and I find out how many multiple choice ones there are, I take that number and I plug it back into my m plus e equals 26, right? So we take away the e, we put a 9 right there, subtract 9 from both sides, so that m equals, in this case here, m is going to be equal to 17, right? So there's 17 multiple choice. So I have my 9 essay and my 17 multiple choice questions on the test. In order to do that, we had to create 2 different equations and then use one to substitute in for the variable that was given there. Okay? All right, number 4. It says these tables correspond to input-outputs. Which of these input-output tables could represent a function rule and which ones could not? Okay, so let's take a look at the next page. We're going to look at some function rules. We have some that are function rules and some that are not. Okay, for it to be a function rule, what we do here has to be the same every time. So this output depends on the input. Okay, so let's think this through. How can I get from a -2 to a +4? I could probably multiply by a -2, right? Or square that to get that to a 4. Let's see if that's what's happening here. Is -1 squared equal to 1? Sure is. What is 0 squared? It's 0. And what is 1 squared? It's still 1. And 2 squared is 4. Okay, so we're going to be squaring the input in order to get the output here. That seems to work. That seems to be a valid function. Over here, we go from 4 to -2. Now that's going to be a little different here. To go from 4 to -2, I think about what I can maybe multiply by, divide by, add by to get there. I'm not quite sure. Okay, so to go from 4 to -2, that's weird. But more importantly, notice that this 4 goes to -2, and when I look down, this 4 goes to +2. I can't be using the same rule and get 2 different outputs, right? So I would say there's no rule here for how this is working. If I put a 4 in the machine the first time and out comes -2, then I put a 4 in later and out comes a +2, the rule is not working properly. So there's no rule there. This would not be a function. Let's look at C. The input is I put 1 in and I get out 0. Put 2 in, I get out 0. 3, I get 0. Well, it looks to me like if I multiply by 0 every time, I end up with an output of 0. So my rule could be multiply by 0. Okay, multiply by 0. And over here, 0, and we get 1, and 0, and 2, and 0, and 3. So this looks like I'm adding 1, adding 2, adding 3. And again, that's not very consistent, is it? It has to be the same pattern each time. So that's not going to be a rule, right? It has a different output, okay, for the same input. And that doesn't work well. So the ones that are going to be part of a function are going to be A and C. Those ones have a function rule. We're good to go. That's it for today. Have a great one. We'll see you next time.